Video, I will introduce the topic of definite integrals and we will solve some problems. Now, at the outset, you will find that the concept of definite integral was already introduced indirectly in a way when we studied the Riemann sums in the previous section. In the Riemann sums, we learned that if you want to find the area between 2 points under a curve, we can divide that area into rectangles and take the sum of those rectangles and use that as an approximation, right? And as we increase the number of rectangles, the approximation becomes better and we get the exact area under the curve. Now, what if some part of the curve is above the x-axis and some part of the curve is below the x-axis? In that case, the concept of area, we have to be very careful how we interpret it. Because if I simply multiply the values of, let's say, the x with the values of y, when the curve is below the x-axis, the y values will be negative. When the curve is above the x-axis, the y values will be positive. And as we add the two things, they will cancel out, right? Then what is integral? What is the area? How to look at the this kind of situation. Okay, so when we get more clarity or when we try to make these concepts clearer, the concept of definite integral becomes more clearer. Okay, so I will again go back to some of these examples which you will find familiar now. Here it says in example 1, interpreting Riemann sums. So the authors here have taken this function f of x equals 1 minus x square, and we are asked to look at two intervals, one from 1 to 3 and the other from 0 to 3, right? The number of subintervals, it's okay, we know, like, we can vary that and make the approximation better. Now let us see what happens in the diagrams. The details you can read. If you want, you can pause the video and read the contents. Let me focus on the diagram. If I'm looking at the interval 1, 3, this function, this part, the graph is here, f of x equals 1 minus x square. From 1 here to 3 here, you can see it goes below the x-axis, and I can use this approximation to compute the area, whatever it is. I think here they have taken 4 intervals and found this rectangles and add the areas of those rectangles and you get an approximate area. Okay, now if your interval is from 0 to 3, in the second case in B, if your interval is from 0 to 3 and you're using 6 subintervals, then your diagram would look like this. Okay, now pay attention to this diagram. This part of the quantity or the area that you are trying to compute is above and this part is below. Okay, so as a result, when we try to add up, let's say this is A and this is B, the areas, there are two things you can look at. One is the absolute value of A and the absolute value of B, and the other one is A plus B, simply adding. Now, when you do a plus b, this is positive, b will be negative. If you do absolute value of a plus absolute value of b, both quantities are positive. Okay, so either we are looking at the total net area between the curve and the x-axis, which is this case, the actual area between the curve and the x-axis. In the second case, we are looking at the net area. Okay, so this is absolute or total area. The one here is called net area. Why do we call it net area? Because if some part is positive and some part is negative, we cancel the positive negative part to whatever extent they cancel out, and what remains, that net area. Okay, will be the second one. And this second interpretation, or this second way of calculating or looking at this, sums of area, Riemann sums, is the concept of definite integral. Okay. Now, if you refine this calculation, if you increase the number of subintervals more and more, and you get more and more approximate area, ultimately, in the limiting case, when the number of rectangles goes to infinity, what you get will be called the definite integral. Okay. That's one clarity we needed there. Now let's move on and look at some example. Like, for example, if your graph f of x is entirely below x-axis, this definite integral, I will also use the notation now, which anyway you will be seeing very soon. This integral from a to b of the function f of x dx. Okay, the definite integral, that is how we denote it. From a here to b here, the limits are from a to b. The function is f of x. Dx is this variable, when you move a small amount here, that's dx. Okay, so basically you are multiplying the values of the function f of x with that dx, so you get the area of that rectangle. This part is the area of one rectangle, and as you add the areas of all the rectangles from a to b, that is denoted by this s, summation or integral notation from a to b. Okay, now what I was going to say is this integral is negative. The output, I mean the number that you get at the end, will be negative because the whole graph is below the x-axis. Okay. All right. Now, when you make the number of intervals, number of rectangles infinite, and you have smoothly adding all of them, you can represent it, without any partition like this. That is, this shaded area here is the integral from a to b of f of x dx. Okay. All right. Now the next concept is evaluating. Now, how do we evaluate? Okay, that is the idea we get when we understand the concept of definite integral. How do we evaluate them? Firstly, there are some facts we need to know. For example, there is a theorem called integrable functions. Okay, what does it say? So basically, the question we are trying to answer is, when does this exist? Just like we asked the question, when does the derivative exist? And we have some conditions, right? The function must be continuous and its limits should be existing, but that's not enough. The left hand derivative and the right hand derivative, or the slopes must be equal from both sides, then the derivative exists, right? In the same way, like if you ask the question, when can I find this integral? The general answer that for all functions is a little complicated and beyond the scope of what we study here. But there are some theorems which tell us which kind of functions are integrable. They're not going to tell you all general cases, but they will give you certain cases. If this happens, then the function is integrable, which means then you can find this integral. Okay. So here, one such theorem is if function is continuous and bounded and finite number of discontinuities, then it is integrable. Okay, now I'll quickly give some examples here. So basically what we want is we want this area to be finite, right? Area to be finite because we have understood this concept that the definite integral is related to the area between the x-axis and the curve, and you need to make sure that two things actually. Number one, that area should be finite, and number two, there should be a way to calculate that. There should be a way to compute that area. Okay, how? If a function is continuous, let me draw some graphs and illustrate this concept to you. If a function is continuous, like, let's say like this, then I can, continuous or bounded, okay? Not and, note that, okay? It is continuous or bounded. Now, the reason they are saying is, if it is continuous, it will automatically be bounded. Okay, that was one of the results in earlier in the calculus. Let me repeat that for your information here. F is continuous on closed interval. Okay, a b like that is a closed interval. This means F is bounded on a to b, and you can prove this very easily using our definition of continuity. Okay, it can be proved. So bounded means basically its values are finite. Okay, it doesn't go to infinity anywhere, right? If it is a if it goes to infinity, then you will have an infinite discontinuity, right? The fact that I am saying it is continuous means it's not going to infinity anywhere, so the values are all finite. And because it is continuous, you can smoothly go from point A to point B, and at the same time always remaining finite. So that means there has to be some max and min value, which you can cap, right? The F doesn't go beyond this and F doesn't go below this. There you can bound it. So it will be bounded. It's kind of intuitive, why this result here is true. Okay, if you just think about it. Now, why being bounded is important? Because if it is bounded, only then you can compute the area as a finite quantity. If the function itself goes to infinity, then the area under the curve from infinity to x-axis, it will not be, you cannot compute it, right? It will be either infinite or indeterminate situation. Okay, so that is the first thing. If f is continuous, then it is integrable. So basically, the first part of this theorem can be simply written this way. Continuity implies integrability. So if a function is continuous but closed interval, that is important, okay? Because we are talking about definite integral from A to B, we have to go from point to point. So continuity implies integrability. That is the basically first part. The second part is actually giving you more relaxed condition. What does it say? Or bounded, let me delete everything that I wrote so far. Please take note if you want to write anything. Okay. And the second part now says bounded on AB. So, or, okay. So if it is not continuous, suppose, then still it can be integrable, but the condition that you need is it has to be bounded. It should not go to infinity, and finite number of discontinuities. So the points where the function is discontinuous, there should be only so many, not infinitely many. Then it is integrable. I'll give an example. Let's say you're integrating from A here to B here, right? And a function could go like this. Let's say, and I might have to make it like this here. This function will be integrable. It is not continuous, but two things are happening. It is bounded. The values are, there is a max value and there is a max in the sense, okay. Now, bounded doesn't mean you can find a max. Okay. In this case, you cannot find the absolute max. Now, if you remember the topic we studied in max and min, you can see this part here. It's going to, this is open here. So the absolute maximum you will not be able to find because it's going and going, but it doesn't, the exact part there is open, right? So there is no definite absolute max, but it is bounded. So bounded is different from being able to find max and min, by the way, a subtle nuance. Okay, if you want to, be very keen about calculus concepts. This function is bounded without an absolute maximum. Why it is bounded? Because there is a value which is larger than all the values of the function, and there is a value which is lesser than all the values of the function. Such a function would be called bounded, right? Actually, because of the line here, it is bounded above. If only that is true, if the values of the function are less than certain value, you call it bounded above. If the values of the function are greater than certain value, you call them bounded above, bounded below, sorry. And if it is both bounded above and bounded below, then you would call it a bounded function, right? If it is bounded and the number of discontinuities is 2 here or infinite, then it is integrable. Now think about it, why this is the case. Why is it integrable? Because the whole concept of integrability is we should be able to compute the area under the curve and between the curve and x-axis, right? Now think about this. You can find this area here, then you can compute this area here, and you can compute this area here. So in each of those intervals, you can compute the area and add all those areas to get the total area. Okay, hence it is integrable. Okay, so that is understanding when a function is integrable. And then here is a concept like I was saying before. In this case, the integral from a to b of the function f of x dx would be 1 minus 2 plus 3. Now, I don't mean the values 1, 2, and 3 as it is, okay? I meant the whatever 1 represents, that area 1, okay? But you have to subtract 2 because it is below the x-axis. Okay? All right. Moving on. That was the figure. Okay, so here is another example. You have a polynomial function like that, and you want to compute the area, integral from 1 to 3. It's that area, and it can be given by this Riemann sum, or when the delta. Understand this also, okay? When delta goes to 0 means the width of the rectangle. The delta there represents the width of the rectangle, delta x. Okay. So when the width of the rectangle goes to 0, that is when the number of rectangles goes to infinity, that Riemann sum becomes the definite integral, right? From 1 to 3 of that function. Okay. So after that, again, here you will see this concept of evaluating the integrals using geometry, which I will show you more in the exercises later. But here I can, you can look at this example. This. If you have to compute the integral, this integral here, right? From 2 to 4 of the function 2x plus 3, you can literally take the graph y equals 2x plus 3, then mark the values at 2 and 4 and draw them down. Now the area of this trapezoid or trapezium, right? Uh, it is called the area of this trapezium is the is that represents that particular integral. Okay, and here is the formula for area of the trapezium, right? What you call half times the width, which is 2, the distance between the two parallel sides, times the sum of the length of parallel sides, 11 and 7. Okay, and the 11 and 7 comes from where? The values of the function. 7 is the value of the function at 2. 11 is the value of the function at 4. And that area is this integral. Okay, so this is an example of computing the definite integral using geometry. Here is another example. In this case, the only concept you have to remember is this area is 9, this part of area is 4, using the areas of the triangle. Then the integral itself would be 9 minus 4. Look at this here. 9 minus 4 equals 5. 9 above the x-axis, 4 below the x-axis. So the integral from 1 to 6, this part here, okay? The integral from 1 to 6, let me remove other part so it's clear. So the integral from 1 to 6 is 9 minus 4. Okay. Here is another example. The function graph is given there, under root 1 minus x minus 3 whole squared. And you are looking at integral from 3 to 4. So it would be this part. Okay. Now you can say that's a quarter of a circle. So 1/4 of pi r square. The area is 1/4 of the area of a circle, which is pi r square. Radius is 1, so pi times 1 squared. Geometry. Okay, if you know this. So if the curve has a good geometry, you can find the integral easily. Okay. Finally, here is a concept of some properties of definite integrals. For example, let's compute this. Okay, integral from a to b is 12. Integral from b to c is minus 10. Integral from a to c will be 12 minus 10, which is 2. Integral from b to d would be minus 10 plus 8, which is minus 2. Okay, I think that what I wrote there is kind of self obvious and also illustrates the concept. Okay, moving on. Now we are looking at some properties of definite integrals. Okay. First property is this. It's interesting concept. Okay. Now why the interpretation is more technical than a real world or a physical exam interpretation. Okay. Why is the integral from a to b to a the negative of the integral from a to b for the same function? Okay. First of all, you need to understand on a axis, okay, A is here, B is here, then integrating from B to A itself is an opposite concept, right? We generally don't think like that. We think of integrating from A to B, from left to right. So when you integrate from B to A, what happens is this changes, the small changes, the delta x that you do on the x-axis would be now negative, right? You would be subtracting. Let's say you're traveling from B to A and you are looking at small increments, okay, small steps from B to A. Then each step you are moving to the left, right? So this delta x will be negative, or in this notation, integral notation, this dx is negative because you are going from B to A and you are decreasing, you are moving to the left. So that change in the value of x, dx is negative. As a result, but the rest of is the, other than that, the area is the same, right? It's the same area under the curve, but except now you are moving from right to left. Hence, you'll get the negative of the original area. Okay, that is the first property. So as I said, it is more technical. Okay. Then the second part is if you uh, apply the same concept here, I think there is a typo. This should have been integral from A to A, not B to A. If you integrate from a point to itself, A to A, that becomes 0. A to A. Okay. All right. Next, constants in the integrals. So some of these properties are again like, kind of intuitive and simple to understand. If you have a constant in your definite integral, you can take it out of the integral process and do the integral of the remaining part of the function only. Because basically, if I'm integrating from, let's say, this function f of x, right? What will be my function 2 times f of x? Would be this. It will only multiply the values of the function, the y values by 2. So as a result, when I'm trying to compute the area, I will be computing twice the area. I'll be computing double area for each rectangle, and therefore the total area also would be double of the original area. So because of that, you can just take that 2 out, compute the area, and multiply the area by 2, right? So that is the constant multiple in the integral. Okay. Then the next concept is integral over subintervals. For example, you want to compute the integral from A to B, and sometimes, this example does not illustrate it clearly, but sometimes your functions change their behavior. Suppose it was like this, and suddenly it became like that. Now, the way you want to compute the area from here to here will be different from the way you want to compute between this, right? So what you can do in that case is compute this as A1, this as A2, and add the two areas to get the total integral. And that is exactly what this equation says. Okay, if you are integrating from A to B, you can take any point P in between and integrate from A to P plus P to B. A to P here, P to B here. Okay, so that is integrating or evaluating an integral by dividing it into uh, smaller intervals or a number of intervals. Okay. Um, So this idea can be used here. What there's like, this diagram, what is being illustrated is, you can compute, use this idea to sometimes even like write, instead of sum, you can also write as a difference, right? If I want to get this integral from a to b, I can get the one from a to p and the one from b to p and subtract. From a to p, if you subtract b to p, you get the part from a to b. Okay. Again, very obvious and self-intuitive. And then the integrals of absolute values. Okay. If a function is an absolute value function, like, then all values become positive, right? Suppose this is the function of f of x, then this should be the graph of absolute value of f of x, right? Where the negative becomes positive. Now this integral, if you do, you'll get everything positive. Whereas over here, you will have a negative part and a positive part, and you have to take the difference. Okay, which means, here's the thing. If someone asks you to find the total area between a curve and x-axis, not the net area, but the total area, what you will do is, you'll take the absolute value of that function, and you will find all these intervals where the function is negative. So take the opposite of it, make everything positive, and add those areas. Okay, that is, if you have to find the total area, the absolute area between the function and the x-axis. Okay, so here is a table or list of properties. The first one we discussed, integral from a to a is 0. The integral from b to a is negative of the integral from a to b. And then the third property says that if you have two functions f and g, adding or subtracting, you can do them individually. This is like in the limits or in the derivatives everywhere, right? If you have a constant number, you can take it out of it, constant multiple, just like in limits or derivatives. And finally, you can break down an interval in two parts. A to B can be broken into A to P and P to B. Okay. And the last one is the concept that I've been talking about. Um, I think at least twice in this video. Okay. The absolute value is the sum of the areas bounded by the curve and the x-axis. So it just takes the sum of the areas. It doesn't do positive and negative. Everything is positive and it just adds the areas. Okay. And then there are examples which I think I can skip because I'm going to be solving problems from exercise in the next video. Okay, I'll pause it here. In the next video, I'll go to the exercises of this topic and solve problems there. See you.